Hello and welcome back to Real Analysis. And as always, first I want to thank all the nice people that support this channel on Steady or PayPal. Now, in today's part 36, we still talk about derivatives. More concretely, we will discuss the chain rule. This one is important when we want to combine two functions g and f in the composition. In a set picture, this means that we first have a function g from left to the middle and then the function f from the middle to the right hand side. And then the combination of both functions is then what we call the composition. And the notation we use for that is f circle g. By definition, this means when we put in a point x into this function, then we have to put the point gx into the function f. Okay, now for the topic about differentiability, we are interested what happens with this property. More precisely, what we want to put in is that g is differentiable at x0 and f is differentiable at y0. And y0 should be the image of x0 under g. Then the natural question is the composition also differentiable at x0? Indeed, the answer is yes, and that is what we will talk about today. So first, let's formulate the chain rule and then prove it. Now, to keep it simple, let's fix two intervals I and j here. So I should be on the left and j in the middle. Hence what we also have is that the function g goes from I into j and f goes from j into r. This now guarantees that the composition f after g is well defined. Okay, now the only assumption we want to put in is that g is differentiable at x0 and f at y0. And now our result is that we have the implication that the composition is also differentiable at x0. In fact, we know even more, we also know how to calculate the derivative. So f after g prime at x0 is given by f prime at y0, which is the same as g of x0 times g prime of x0. So the derivative of the outer function f gets multiplied by the derivative of the inner function g. Indeed, this is one of the most important rules we have in calculus. Simply because we often have such combinations of functions. Therefore, you also often see this chain rule with another notation, which might be easier to remember. There, the derivative is written as d by dx, which means we also have to specify the point x0 here. And usually this is done with a line on which we put x0. In the same way, we can do this on the right hand side where we introduce the variable y for the function f. And there the given point we should specify is g of x0. And then the only thing that remains is times dg by dx at the point x0. Okay, now the reason why people like this formulation is because it looks like fractions where you can cancel out these two terms. Of course, actually this is just a mnemonic trick to remember the formula. So maybe it helps you to remember the two key elements here. We have an outer derivative and an inner derivative. Okay, with this I would say, let's prove it. Of course, this proof should work similarly to the proof of the product rule from the last video. In particular, by assumption, we can use that we can write the function g in this way. Here we have a continuous function delta, where the limit x to x0 gives us exactly the derivative. Then obviously we have the same formulation for the function f, but there we should use another variable we call y. Because for f we work in the domain j. For this, please don't forget, y0 is given by g of x0. So there we have everything and we can put it together. So let's look at the composition at a given point x. Now the first thing you should see is that this g of x is a point y in the interval j. Or in other words, we simply can use this formula we have for f. The only thing we change is that y is now g of x. So you see, since g of x comes in here, we can substitute it with the formula we have for g. Hence we also get in the term x minus x0 we need for the composition. So now we have added these terms here and you can immediately see g of x0 and y0 cancel out. Therefore we see what remains is exactly what we want. Here we have the factor x minus x0 and here are the two derivatives. More concretely, here we have a well-defined function that is continuous at the point x0. And as always, the limit x to x0 will give us the derivative. Now, if we want, we can give the function the correct name, and then you see this is the linearization of the composition. Hence, now our conclusion is the composition is differentiable at x0. And we know the derivative we get when we calculate the limit x to x0 of this function here. Hence, it means here we have the derivative of g at the point x0, and here the derivative of f at the point y0. Therefore, you see this is our chain rule formula, just with changed order. And with this, our proof is finished. Okay, then in the next video we can look at examples for all these rules. Therefore, I hope I see you there and have a nice day. Bye!